Welcome to the third lecture. In this lecture, we're going to talk about nonlinear system analysis. Now, we have already seen before that whenever we talk about control systems, we start with analysis of control systems, in which we basically study the properties of various systems. We analyze their behavior, and then from analysis, we move on towards designing a controller or design of control systems to attain certain engineering objectives. Now, in a similar way, for nonlinear control systems, the first part is analysis, and we'll be basically studying three different techniques for analysis of nonlinear control systems. And by analysis, we mean that, for example, we have a system, we have a nonlinear control system, and we know the input, so we are basically interested in the output, and we are also interested in what happens to the states inside the system, right? Okay, so what are the different techniques that we'll be studying in this portion of the unit? One is the phase plane analysis, right? Phase plane analysis. The other is Lyapunov theory. And the third technique is called the describing function method. Phase plane analysis is primarily analysis of second order nonlinear systems, or systems that can be approximated by second order nonlinear systems, and it's a graphical method which tells us about various properties of the system, like the trajectory of the state trajectory, like the equilibrium points of the nonlinear system, whether or not there are limit cycles present in the nonlinear system, and so on and so forth, right? Lyapunov theory concerns mostly the stability analysis of nonlinear systems, and is basically, there are two methods in this. One is called the direct method, which analyzes the linearized system, right, to talk about the stability of the nonlinear system. And the indirect method, which talks about the linearized system and how analyzes the linearized system and then predicts the stability of the nonlinear system. And the other is the direct method, which constructs a function called the Lyapunov function for the nonlinear system. The third technique for analysis is the describing function method. And in the describing function method, this is also an approximate technique. This is an approximate technique for studying nonlinear systems. And herein, what we basically do is that we approximate the nonlinear system by linear equivalence. Again, we use linear equivalence to approximate the nonlinear system, but the difference is that we use frequency domain methods that have been perfected in the linear control systems domain. We use those frequency domain methods to analyze the resulting linear equivalence. Right? So this was a brief idea about what we are going to study in this unit. So we are in this part of the fifth unit. So we are going to start with the first technique, which is the phase plane analysis. Right. So as I said before, this is a graphical method which is applicable to second order nonlinear systems or to systems that can be approximated by second order nonlinear systems, right? So what would a second order nonlinear system look like? Right, let us first look at the formulation for a second order nonlinear system. So as I've told you in the first lecture, the systems that we're talking about have this general form x comma u, explicitly defined x dot, right? Although this is not general, but it is sufficient for what we are trying to do in this unit. F is a nonlinear function of x. X belongs to the n-dimensional space, and u is the input. U would belong to the p-dimensional space if there are p inputs. And we basically study, as we do in the linear case, we first study the homogeneous equation, right? So we have a system x dot is equal to fx, which does not have an input. So we study the homogeneous system first, and then we extend the results to non-homogeneous systems. So our basic function is x dot is equal to fx. Now since we are talking about second order systems, x actually belongs to r square, because the order of the system is equal to the number of the states of the system. So if x belongs to r square and we want to just open this up, that means x is actually a vector x1 x2. So if you open this equation, it's going to look something like this: x1 dot is equal to f1 x1 comma x2, and x2 dot is equal to f2 x1 comma x2, right? And f1 and f2 are nonlinear functions of the states. So this is the typical second order nonlinear system that we'll be looking at while we are doing phase plane analysis, right? So now some definitions before we start making the phase portraits and doing the phase plane analysis, right? So if basically what is a phase plane? Simply said, if you sketch these two state variables x2 and x1 along the x and the y axis, this plane that you get is called the phase plane, right? So the phase plane is a plane having x1 and x2 as coordinates, right? Now given a set of initial conditions x0 x is equal to x0 is equal to x0, the states would evolve in the phase plane, right? What does that mean? That means the states would change from their initial conditions to some different values. So like if you have x0 is equal to x0, which means x0 is equal to x0 actually means x10 has some value, right? Say x10, and x20 has some initial value x20, and then these states would evolve, because this is a dynamical system. Everything is would change in time unless and until you settle down at some equilibrium point. So these states start from these initial conditions and then they evolve, and when they evolve, that means you can basically start from some initial conditions, say here in the phase plane, and then you can sketch the evolution of the system as the as the values of the x1 and the x2 states change. So this sketch that you draw is called the phase trajectory. So this line is the phase trajectory, and this is the phase trajectory. This is the phase trajectory for the initial condition x0 is equal to x0, right? So uh, if you want to define it, you can say that given a set of initial conditions uh, with time varying from say 0 to infinity, the solution xt can be represented geometrically as a curve in the phase plane, and that curve is the phase trajectory. Now this phase trajectory would be the trajectory for one particular initial condition. If you have a number of different initial conditions, then you can sketch different phase trajectories. Suppose with a different initial condition, your states evolve like this. For different another initial condition, your states evolve like this. Then this portrait that you get is called the phase portrait. So a set of phase trajectories, each corresponding to different initial conditions is called the phase portrait. Right? So basically three definitions that we have seen. We have seen what is the phase plane. These are simple definitions. Phase plane, we have that's the plane in which the coordinates are the states of the second order system. We have seen what is a phase trajectory, where we are trying to sketch the trajectory in which basically the system starts from some initial condition, right, and then evolves, the states evolve, and we are sketching the states. And the third is the phase portrait. Now please understand that this phase trajectory would be different from this sketch that we have been doing. We have been trying to plot x1 with respect to time, and we have been trying to plot x2 with respect to time. Now here we are not doing that. We are not plotting, although these both of them are functions of time actually, and we have been till now looking at plots with respect to time, whether of states or of outputs, but in this case we are talking about plotting them on a plane in which the coordinates are x1 and x2. So we're plotting x2 with respect to x1. So there's a difference. I hope you have got the point, right? Now let us take an example to see how this could be done for say a simple system, right? Let me take a very simple, I'll take a linear system because we can draw this for linear systems also. So let me take a mass and spring system, right? So there's a mass, there's a spring here, right? And let us assume that the mass is 1 kilograms, the spring constant is also 1. So this becomes a simple system, and there is no friction, the friction is absent. So if you look at the differential equation of the governing the system, where the displacement is x, the differential equation would be x double dot plus x equal to 0, right? For a general mass spring damper system, your differential equation is mx double dot plus d, where d is the friction, x dot plus kx equal to 0. So this term is absent, and m and k are 1. So the equation is this one, not x dot, sorry, x double dot plus x equal to 0, because there is no term corresponding to friction. Now this is a second order system, right? This is a second order system, and it is a linear system, right? But we can draw the phase portrait for this. So if you solve this x double dot plus x equal to 0, right? Let us first see what are the states. What are the states? This is a differential equation. So what are the states? So if you remember, there would be two states for this. One would be x and the other would be x dot. So there are two states for the system, x and x dot. This is how we convert from a differential equation to the state space form. The easiest method of converting from one form to the other. So the states are x and x dot. Okay, so let me call this state x1 and let me call this state x2, right? So these are the two states of the system, and what I want to do is I want to plot this x2 with respect to x1, right, which is actually x dot with respect to x, right? So let us first look at the solution for this, right? This is a typical differential equation which is linear. It's very easy to solve. I won't go into the details of solving this. So this is something that you know from your network analysis course also. So if you have this differential equation and you have initial conditions, say x0 is equal to x0 and x dash 0 is equal to 0, two initial conditions, then you can very easily solve this. It's a homogeneous differential equation. To get the solution would be x is equal to x0 cos t and x dot is equal to x0 sin t, right? Okay, so now this is the solution to the differential equation, in the sense that we are getting the evolution of the states from the differential equation, right? Now suppose I want to plot, if I plot x with respect to time, I can do that, right? It's a cosinusoidal function of time. If I want to plot x dot with respect to time, I can do that. It's a sinusoidal function of time. But what I want to do is I want to plot x dot with respect to x for some initial condition, right? Okay, so I can do that if I get x dot as a function of x, right? So, we have some direct functional relationship, and we can get that by eliminating t here in this. Eliminate t. So how do I eliminate t? I can just square and add these two equations. So I square this and add the two equations up. You get x dot square plus x square is equal to x0, right? And in terms of x0 square, and in terms of the state variables x1 and x2, I get x2 square plus x1 square is equal to x0 square. Now this will help me draw the phase portrait, because what this tells me is that if I plot x2 with respect to x1, it's a circle of radius x0. So for an initial condition x0, right, remember this is x, the x-axis is x, the displacement, and the y-axis is velocity, right? So for an initial condition, initial displacement x0, which was the initial condition here, and an initial velocity 0, which is the condition here. So the initial displacement is x0 and the initial velocity is 0 at this point. What I get is a circle, right? So I've on the phase plane for this second order system, I have sketched the phase trajectory, right? This is a phase trajectory for my initial condition x0. Now I can do one more thing. I can also look at the direction from this, although the direction is not evident from this equation, but we know that if we start from this point, right, x0 cos t, as time proceeds, this displacement is going to reduce, right? So the x0, you start from a high value cos t, initial value 1 when t is equal to 0, and then as when t becomes pi by 2, this displacement would be 0. So you move in the direction of reducing displacement and increasing velocity. So that direction, if you start from here, reducing displacement, increasing velocity, right, would be this. You'd say it could also be this, but you have to see that as x1 as because we have written x dot scale is equal to x dot scale plus x scale is equal to x0 scale. So as the velocity becomes more and more negative here in this in this case, so the displacement has reduced. Okay. So this is for one such case, or let me do it slightly more effectively. So let us say that x is equal to x0 at t is equal to 0, right, and x dot would be 0 at t is equal to 0. So that is this point here, and what is going to happen at t is equal to, say, pi by 2. At t is equal to pi by 2, x is equal to 0. So as time proceeds, x becomes 0, and what is x dot? X dot is equal to going to be minus x0, right? I forgot the minus sign here, sorry. Right. It's minus x0. This is the solution because if you differentiate x0 cos t, x dot would be minus x0 sin t. So this minus sign is there. So the next point is 0 minus x0. So you start from this point, and the next point is going to be the point where your displacement is 0 and your velocity is minus x0. So this is minus x0, right? So that is why the arrow is in this direction. So you start from one initial condition, you get this, and if your initial condition changes, suppose your initial displacement is more, that means the radius would be more. So it's going to be like this. And suppose you start with an initial condition in which your radius is less, so you'll get a circle like this, and your arrows in the same direction. So this is the phase portrait. Right? This is the phase portrait for the second order system, which is a linear system in this case. Now a little more about what happens. For example, now we did this for a linear system, right? And what we can immediately understand without actually looking at the solution is that this is a marginally stable system because you have sustained oscillations. It's a marginally stable system. And why is that? Because you can see that the displacements x1 and the velocity x2, they are continuously oscillating, right? The values reach a maximum. Say for example, the value of the displacement is maximum here, then it becomes 0, then becomes maximum in the negative direction, then becomes 0 again. And similar for the velocity is maximum in the positive direction here, and then the velocity becomes 0 here, then it becomes maximum in the negative direction here, and then 0 in the negative direction, 0 here, right, and then again maximum here. So you can see that there is oscillation, and the oscillations are not dying. It is not something like start oscillations and these oscillations die. If this happens, then that means the oscillations are over. So you can just by looking at the graph, you can visualize and say that this is sustained oscillations, right? You say this is sustained oscillations, and you can straight away guess that the system is a marginally stable system, right? So in a similar way, when you draw phase portraits for your nonlinear system without actually solving it, right? In this case, yeah, we solved the linear system, we got the solution, right? But in the nonlinear, there are other ways of actually drawing the phase portraits without actually solving the nonlinear system. Draw the phase portrait, and you will be able to then analyze the behavior like this, right? So we'll be looking at these methods in more detail in the second part of this lecture. Thank you very much for listening.